In section 5.5, we're going to be looking at alternating series. That is, series whose terms alternate in sign, either positive, negative, on towards infinity, or starting negative, positive, negative, positive. So we have two examples here. In this first example, we have the definition of a series that will start positive. So generally speaking, when we have a negative 1 raised to the n plus 1 power, we're going to start with a positive term. Here, where we have negative 1 raised to the n term, we start with a negative. And so we're going to see these two definitions, or two different forms, as a part of our definition of an alternating series. So let's take a quick look at a couple of examples and get on to the alternating series test. So in the first example, we have negative 1/2 raised to the n power. Now, again, you could think of this as 1/2 times negative 1 to the n power, right? And so this is our alternating part. This is the part of the series that is making it alternate. And so we end up with a negative, positive, negative, positive. In this particular case, our basic function is just 1 over n, but 1 over n is being multiplied by negative 1 to the n plus 1 power. Okay, so when we take a look at these functions, what we want to do is we want to isolate the part of the function that is making it alternate from the part of the function that, or the series, that is not alternating. In other words, we want to determine what the b sub n is. The b sub n is the non-alternating sequence in each of these, and then the negative 1 to a power is what's making it alternate. So if we have an alternating series in either one of these forms, then the series will converge if these two things are true. Number one, it has to be a decreasing function. It has to be a decreasing function. And what we're talking about here is 0 is less than equal to b sub n plus 1, which is less than equal to b sub n. Now remember, the b sub n here is the non-alternating part. It's the sequence. Okay, it's the sequence. So in this example up here, the b sub n is the 1 over n. In the previous example, the b sub n is the 1/2. It's the part of the series that is not causing it to alternate. And the second thing is that the limit of b sub n has to be equal to 0. So if it's a decreasing function and the limit is equal to 0, then it is going to converge by the alternating series test. So what's really going on here is, if I just draw a couple little pictures down here, we know like a sine function is alternating. It goes up to 1, down to negative 1, up to 1, down to negative 1, up to 1, down to 1, up, back and forth. All right, it never converges. It just keeps going up and down from 1 to negative 1 infinitely far. So it does not pass either one of these two criteria. The limit is not 0, and it's not a decreasing function. On the other hand, we can have a function that is doing this. It's getting bigger and bigger and bigger and bigger and bigger, and so it's clearly diverging. It does not have a limit of 0, and if we were to just take a look at all the tops of this, it's growing, it's getting increasing. It's an increasing function if we just look at the non-alternating part of it. So what we're looking for is a function that, even though it's alternating up and down, that it is the fluctuations in up and down are getting smaller and smaller and smaller and smaller. That's the type of function, if we can show that if we were to eliminate the alternating part of this, and so if we just kind of like took a look at the tops of each curve, and we can see that it is decreasing, and it is decreasing towards 0. The limit is 0. So this is the type of function, if we can show that these two things are true, that it will be a converging series by the alternating series test. All right, so let's just do a couple examples. First of all, here's our series. And so what we want to do is we want to determine what B sub n is. All right, so what is B sub n? Well, B sub n over here is 1 over n squared. So you get rid of the part that's making it alternate, which is the negative 1 to the n plus 1, and what you're left with is 1 over n squared. That's your B sub n, the non-alternating part. So if we can show that the non-alternating part is decreasing and the limit is equal to 0, then it converges by the alternating series test. So first thing we do is show that it is a decreasing function. And we did this in a prior section. And so what we want to do is say, okay, well, is 1 over n plus 1 squared, we're just adding 1 to the n, less than or equal to 1 over n squared. Cross multiplying, we get this. And now intuitively, we can see that n squared has to be less than or equal to n squared plus 2n plus 1. And so it passes the first requirement by the alternating series test. I just like to put a little check there. Number 2, we have to show that the limit is equal to 0. So the limit of 1 over n squared is clearly equal to 0. Right? Just taking the limit of that, boom, it passes requirement number 2. So B sub n is decreasing function. The limit of B sub n is 0. Therefore, the alternating series converges. Second example. In the second example, they've kind of separated out the alternating series from the B sub n for us. So here's our B sub n right here. All right, because this is what's making it alternate, the power of negative 1. And so number 1, we need to show that B sub n plus 1 is less than or equal to B sub n. And so if you take n and add 1 to it, you get n plus 1 over n plus 1 plus 1, or n plus 1 over 2. And is that less than n over n plus 1? Cross multiplying, we get this. And then to make it a little bit clearer, let's multiply terms together. We get this. And so we have n squared plus 2n plus 1 is supposed to be less than n squared plus 2n without the plus 1. Clearly that's false. Okay, because that is false, it's not going to pass the alternating series test, and therefore the series diverges. But also let's take a look at the limit. Requirement number 2. If we take the limit of n over n plus 1, our B sub n, the limit is equal to 1, which is not equal to 0. And so therefore it fails both parts of the alternating series test, and therefore the alternating series diverges. If it fails either part, I didn't really need to do both parts, but I just did it to show it, to demonstrate. If it fails either one of these two requirements, it will diverge. Okay, and another example. So we know that cosine of n pi, so in other words, cosine of pi, cosine of 2 pi, cosine of 3 pi, cosine of 4 pi, is an alternating series because it alternates between negative 1 and 1. All right? So the values of the cosine of n pi are constantly fluctuating between negative 1 and 1. Question is, if we take that, divide it by the square root of n, is this entire series now going to converge or diverge? It is an alternating series. It's the numerator that makes it alternate. So therefore, the B sub n, in this case, B sub n is simply 1 over the square root of n. It's the non-alternating part of this series. And so we have to show that B sub n plus 1 is less than or equal to B sub n. And so we simply add 1 to the n, so we get 1 over the square root of n plus 1 is less than 1 over the square root of n. And once again, cross-multiplying, it's a little bit easier to see. The square root of n is going to be less than or equal to the square root of n plus 1, because this is always going to be a little bit bigger, so its square root is always going to be a little bit bigger than that. So check, it passes requirement number 1. And of course, finding the limit is easy. The limit of 1 over n squared is equal to 0. It passes both requirements for the alternating series test, and therefore it converges by the alternating series test. And that's pretty much all there is for the alternating series test, is that you just have to be able to show that b sub n is decreasing and show that the limit is equal to 0. All right, one more quick thing for this video. There may or may not actually be any homework assignments on this. I just want to pass it by you so you are aware of it. This is called the remainder of an alternating series. And so here's our basic definition of alternating series in either one of these forms. And so what this is saying is that for any integer capital N greater than or equal to 1, the remainder of n, so if n is equal to 10, then r sub n, the remainder is equal to the sum of the series minus the nth partial sum. So over here, s sub n is the nth partial sum, and so r sub n is basically the remainder of the nth partial sum. So we're looking for the remainder of the nth partial sum. And so here's what we really need to be looking at right here, because we're generally not going to be able to find the sum of the series. The remainder is going to be equal to the sum of the series minus the nth partial sum. Well, that would be very difficult to find out. But this basically says the absolute value of the remainder of the nth partial sum is less than or equal to b of n plus 1. So it sounds a little complicated, but if you just take a look at this first example, it really is not all that bad. So in this particular example, it says use the remainder estimate, determine a bound for r sub 10. That would be the remainder of the 10th partial sum, if we approximate the sum of the series by using the 10th partial sum. All right, so what this is saying is that the remainder of the 10th partial sum has to be less than or equal to b sub n evaluated at n capital N plus 1. Well, n in this case is 10. Okay, n is equal to 10 because that tells me what n is. That's r sub n. So n is equal to 10. So this is saying that the remainder of the 10th partial sum is less than or equal to my b sub n evaluated at 1 more than capital N, which is 11, so it has to be shown that it's less than or equal to b sub 11. So what that means is that we evaluate 1 over n squared, where we substitute 11 in for n, 1 over 11 squared. Well, 1 over 11 squared is 0.008265. And so what this is telling me is that the absolute value of the remainder of the 10th partial sum is going to be less than this amount. It's an approximation. It's not an exact, it's an approximation of that. And so it's a quick and easy way to get an approximate value. And so I, for some reason, wrote these various definitions back down here again. All right, if necessary, I will do another video with a couple more examples of this on it. I think that should suffice. If not, let me know. All right, that's it for this video.